Hello. So there was a question today during our review about if we could look at a more complicated problem with momentum conservation, and I think that was a good idea. These problems tend to be a little more involved, so I'm just going to make it into its own video. Uh, just 1 second. Let me see if the stream is working here. Okay, so you can see the problem here. We have a billiard ball traveling at uh, 3 meters per second, collides perfectly elastically with an identical billiard ball initially at rest on the table. The initially moving billiard ball deflects to 30 degrees. What is the speed of the initially stationary billiard ball after the collision? So this is a pretty classic type of problem in terms of momentum conservation problem in 2 dimensions. Um, let's give ourselves a little bit of a cartoon to try and start figuring out what's going on here. So we have a billiard ball traveling at 3 meters per second. Let's call that VA. Um, and let's call this MA. Although it says that they're identical, so the masses are going to be the same, but let's just keep it in there for the time being. And then it's going to collide with an identical one, B, so its velocity would be 0 because it's stationary. And then after, we're going to have, there's a collision, and we have one ball that's traveling off at an angle of, let's call this angle theta, 30 degrees. And this would be the original ball that was moving. So this is VA prime. And then the other ball is traveling off at some angle. Let's call it alpha. This would be VB prime. So what else do we know? We know that this is an elastic collision. Perfectly elastic, meaning that the kinetic energy initial is going to equal the kinetic energy final. What do we not know? So we also know in the collision that momentum is conserved. So the momentum initial is going to have to equal the momentum final. What do we not know? The eraser isn't working. That's weird. So there's actually a lot of things that we don't know in this question. All that we're given is the angle for VA prime. We don't know VA. We don't know, sorry, VA prime. We don't know VB prime, nor do we know the angle alpha. And the one that we're interested in is what is the speed of the initially stationary ball after the collision. So that would be VB prime. This is really what we're trying to find. So let's start laying out some momentum and energy conservation equations and see what we have to work with. So if we look at the momentum conservation in the x direction, so I should say I should have a coordinate system going here too. So we're going to assume that these were initially moving along the x-axis. The sum of the momentum in the x initial is going to have to equal the momentum in the x final. So what does that look like? We have MA VA is going to equal MA VA prime. So we want the x component of VA prime, so that'll be the cosine theta piece, plus the contribution from VB, or MB rather, which will be similar, MB VB prime cosine alpha. And then making use of the fact that MA equals MB, we can simplify this, divide out by a factor of m, in other words, and we have an expression, the following. Basically, that VA equals VA prime cosine theta plus VB prime cosine alpha. Okay, so let's look at the momentum conservation in y. So in this direction, there is no momentum in the y direction to begin with. So 0 is going to equal VA prime, MA VA prime. Now in the y direction, that'll be the sine piece, plus MB VB prime sine alpha. And similarly, we can make use of the fact that the masses are the same and rewrite this as VA sine theta plus VB sine alpha equals 0. And then let's also look at the kinetic energy. So the kinetic energy initial has to equal the kinetic energy final, means that this is an inelastic, or perfectly elastic collision. And in this case, well, what all pieces do we have? We'll have 1/2 MA VA squared plus, well, that's going to equal 1/2 MA VA prime squared plus 1/2 MB VB prime squared. VB not contributing to the initial kinetic energy because it has no initial velocity. Now, notice a bunch of this is if we make use of the fact that the mass is the same for both, we can cancel a bunch of this. And so we have VA squared equaling VA prime squared plus VB prime squared. So we have 3 equations and 3 unknowns. Let's label these equations. We're going to try and figure out how we can put these together to solve for VB prime. So let's call this equation 1. Equation 2. Equation 3. So this gets at what I have described to you before a little bit, in that conceptually this is not that complicated. We've just looked at momentum in x and y and the conservation of kinetic energy. But it's kind of complicated algebraically because we have 3 expressions and 3 unknowns. So there's no one right way to go about this, but basically we want to try and eliminate the things that we don't want. So we want to try and eliminate alpha and VA prime. So eliminating alpha is sort of tough. We could substitute in, if we divide, we'll just get tangent alpha or cotangent alpha or something like that. So that wouldn't necessarily eliminate it. It's complicated by the fact that it's inside the trig function. So here is one approach. Let's make use of, let's try and combine 1 and 2, making use of the fact that sine, sine of an angle squared plus cosine of an angle squared equals 1. So this would allow us, if we have cosine, we can express cosine alpha in terms of this other stuff. We can express sine alpha in terms of that other stuff. And we can combine them together, and that'll equal 1, and that will allow us to eliminate alpha. So let's give that a shot. So from 1, we can write cosine alpha as VA minus VA prime cosine theta divided by VB prime. This is cosine alpha. From 2, we can write this as, notice this will be negative VA sine theta divided by VB. Actually here, this should have a prime on it, as should this one. So this will be, VA prime sine theta divided by VB prime equals sine alpha. Okay. And then we can square both of these pieces and add them together, and then that would add up to 1. So if we do that, we would have VA minus VA prime cosine theta divided by VB prime quantity squared plus negative VA prime sine theta divided by VP prime squared equals 1. So we've gotten rid of alpha, but we still have kind of a mess that has both A prime and VA prime and VB prime in it. So let's see if we can eliminate one or the other of those. And so let's expand this. And let's multiply over by a factor of VB. Let me just reorganize this a little bit. So if we expand this and we multiply by a factor of VB prime squared, we would have following. Let me copy this and write it over here as well. So let's expand this a little bit. Let's see what happens. So if you FOIL this thing out, you'd have VA squared minus 2 VA prime cosine theta plus VA prime squared cosine squared theta plus this thing we would pick up a factor of VA prime squared sine squared theta equals VB prime squared. So notice we're trying to get VB prime, but we have a thing that's quadratic in VA prime, so it's going to be difficult to get that, eliminate that. Instead, we have VB prime squared by itself, so we could eliminate that. Let's do that. So we can also notice there's some simplifications that we can put in place here. So basically, let's factor out a VA prime squared. We can factor that out from both of these terms, from a cosine squared plus sine squared. Like we used this before, this is 1. Now, VB prime, we can, from equation 3, notice that VB prime squared is VA squared minus VA prime squared. So let's stick that in here. So making a substitution from our kinetic energy expression. So now we have something that only has VA prime in it. And everything else we know. So we can solve for VA prime and then put back in for VB prime. So, or that's the idea anyway. Notice some stuff is going to cancel. There's a factor of VA squared on both sides that we can cancel out. And then let's rewrite this and see what we have here. So we have and then notice also we have 2 factors of VA prime squared. So let's put them all on the same side. We have 2 VA prime squared minus 2 VA prime cosine theta equals 0. So this is really collapsing down. Notice we have a factor of 2 that's common. We can cancel. We also have a factor of VA prime that's common to both of these, so we can cancel that. And we're left with VA prime equaling 2 VA cosine theta. Or sorry, not 2, just VA cosine theta. And we know VA, we know theta. We can compute what that is. So this is a nice, concise result for VA prime. So if we know now VA prime, we can get VB prime from, I think, in a variety of ways, but equation 3, or I suspect you could do it in different ways, but equation 3 seems to jump out. So notice we can substitute in for VA prime, and then we'll be left with an expression that just has VA and VB. So then we could subtract, move stuff around here. We would find VB prime squared would be VA squared minus VA squared cosine theta squared. And then we would take a square root of that, and we could factor out also a factor of VA squared, 1 minus cosine squared theta. So VB prime would be a square root of that situation. So in other words, VB prime would be VA times the square root of 1 minus cosine squared theta. Notice cosine squared, like we used before, 1 minus cosine squared is the same thing as sine squared, so this thing becomes VA sine theta. So now we have an expression for VB prime. VB prime would be VA. Putting in our numbers, VA was 3 meters per second. Theta was 30 degrees. So this becomes all of this algebra just to show that this becomes 1.5 meters per second. So there you go. That's an example of momentum conservation in 2 dimensions. A little more complicated example, we had 3 equations and 3 unknowns. We did some trig relationships to eliminate an angle, and then we did some substitution to get an expression that was just for what we wanted, and found the velocity that we were looking for. So I hope that that's helpful for you to see one of these more complicated problems. It's definitely a little more just algebra. It's good to practice them. Make sure that you have ideas for different algebraic approaches. Like I said, it's not really that complicated conceptually. We're just looking at momentum conservation in x and y and energy conservation. In this case, being that it's an elastic collision. But the algebra can get a little more complicated than the stuff that we have done, so, or than most of what the kinds of problems that we look at. So I hope that's useful, and have a nice day.